So in this problem, we need to show that E is real. And if you recall, you can represent any number, any constant, as a real portion, which we'll denote as E naught, and a complex portion, which we'll denote as I times gamma. So if we want to show that E is real, we need to show that gamma is actually 0. Additionally, the problem asks us to find it under 4 normalizable solutions, which is just another way of saying that whenever you integrate the probability density over all space, that it equals to 1. In other words, if you add up all of the probability of finding the particle over all space, it equals to 1. You have to be able to find the particle somewhere. So the first step is expressing the wave function in terms of this separation constant that we have here. So when we do that, we can express the wave function, which is both spatial dependent and time dependent, as just some spatial dependent portion, which is we'll denote as little psi as a function of x. And then if you recall earlier in the chapter, we did the separation of variables, and the spatial time dependent was some exponential, some negative complex exponential, which is negative I times E times T over H bar. Now we substitute our E into the E that we have into the time dependent portion. We'll get this. And then you do some algebra distributing that, you'll end up finding this next expression. So here we, of course, have our spatial dependent portion, and then we have a time dependent portion, which includes both our gamma and our E naught here. And if you notice, this one has no complex I in it, because whenever you distributed the I, it became -1, which made this negative sign positive. So now whenever we substitute this wave function in under this expression here, the normalizable conditions, we'll get something that's a little bit more telling of where the problem will go. So whenever you do the modulus squared of this portion, that's just going to be the modulus squared of the spatial dependent portion here. Because we don't have an actual expression for this, we're just doing it in general wave function terms. But we can do something with this portion here, this whole area here. So remember, whenever you do the modulus squared of something that has a complex number in it, you just flip the sign on that and multiply it by the original complex that we got. So I'll just put this one in parentheses here. So it'll be positive I E naught T over H bar times our, we'll just get rid of that times, our original complex exponential. So that does it for that one there. Now we do it for this one. So this one is when we take the modulus squared of this, that one doesn't have any fancy i's or anything in it, so it's just going to end up being E2 times gamma H bar over H bar. And this is all over dx, right? Now, it's important to note that at this point, this is only an integral over space, so that means anything that is time dependent can move outside of the integral. So for the sake of time, let's just do this actually. Well, actually, before we do that, you notice that this is actually just going to be equal to 1 because it's the same thing in the exponential except for different signs here. So that all equals to 1. But this will come out in front of the integral. And so remember, so for normalizable conditions, this all has to equal to 1. So now we have to be able to make this fit our normalizable conditions, also known as, like, if you integrate the probability density over all space, so negative infinity to positive infinity, it's got to equal to 1, which means, so if this all equals to 1, this all has to equal to something. It's got to equal to 1, right, to be able to make this fit under the normalizable conditions, which means that this up here, this has to actually equal to 1. And the only way for that to equal to 1, knowing that this is a constant, this is our time-dependent variable, and this is a constant, the only thing that we can fudge is gamma, which means that gamma actually has to be equal to 0. Also known as, when we go back up here, that E has to be real because gamma is forced to be 0 to make this all fit under normalizable conditions.